Here's a scenario that trips up almost every GitHub Actions beginner. You push a commit. Your workflow fires. Two jobs start, one called build, one called deploy. They both run at the same time. Build succeeds, deploy fails. You check the logs and realize deploy was trying to use a file that build had created, but the file wasn't there. Why? Because build and deploy were running on completely different virtual machines. Two separate computers. Neither one could see the other's file system. This is the core mental model of GitHub Actions execution model. Jobs run in parallel by default, each on its own isolated, ephemeral VM. They don't share memory. They don't share disk. They don't share anything. In this chapter, we're going to build a complete mental picture of how the execution model works, from what a runner is, to how jobs depend on each other, to why artifacts exist, to the advanced patterns like matrix builds and self-hosted runners. By the end, you'll understand exactly what happens the moment you push a commit, and you'll never be surprised by a missing file again. A runner is a virtual machine. That's the simple version. GitHub spins one up on demand, specifically for your job, runs your steps, and then destroys it. You never see it. You never SSH into it. It exists purely to serve your workflow job. Here's the lifecycle in order. You push a commit. GitHub sees the workflow trigger. It queues your job and provisions a fresh VM somewhere in Azure's infrastructure. That VM clones your repository, runs each of your steps in sequence, and when the last step completes or fails, the VM is terminated. Gone. No trace left. The word fresh is critical here. Every single job run gets a completely clean slate. No leftover files from the previous run. No cached environment variables you didn't set yourself. No mystery state from 3 weeks ago. This ephemerality is what makes GitHub Actions so reliable and reproducible. Your workflow either works on a clean machine or it doesn't, and that's exactly the truth you want before shipping to production. The only thing you control is the key, which OS and machine type gets provisioned for your job. GitHub maintains 3 operating system families for hosted runners. You choose between them using the key. Ubuntu is the workhorse. It boots fastest, costs the least, about half a cent per minute, and supports virtually every modern development tool. If you're not sure which runner to use, ubuntu-latest is almost always the right answer. Windows runners are there when you need them: .NET builds, PowerShell scripts, Windows-specific installers. They cost about twice as much as Ubuntu. Mac OS runners are specialized. If you're building an iOS or macOS app and need to run Xcode, you have no choice. But be aware, they cost roughly 10 times more than Ubuntu. Use them only where you must. Now here's the gotcha with the latest suffix. When you write, you're using an alias. GitHub periodically updates that alias to point to a newer OS version. When they do, your workflow silently gets a different operating system, and things that worked before might suddenly break. For production workflows, the best practice is to pin your version explicitly. You can always intentionally upgrade. Surprises in production are never fun. Here's something that surprises most people: the fresh VM isn't a bare Linux installation. GitHub pre-installs an enormous suite of software so you can skip setup for the majority of projects. Node.js? Already there, multiple versions, managed with tools like NVM. Python 3? Pre-installed. Java with multiple JDK versions? Pre-installed. Ruby, Go, PHP? All there. Docker? Ready to go. Git, curl, Git, JQ, the AWS CLI? All available the moment your job starts. This means for most web projects, your workflow can go straight to the work, check out the code, run npm install, run your tests. No install node step required. The full software manifest, every installed package and its exact version, lives at github.com/actions/runner-images on GitHub. It's worth bookmarking. When something breaks after a runner image update, that's your first debugging stop. When you do need a specific version, say Node 20 exactly, or Python 3.11 specifically, use the official setup actions, and so on. They layer the right version on top of what's already installed. Think of the pre-installed software as a generous starting kit. It gets you 80% of the way there with zero configuration. A job is a named unit of work that runs on a single runner. Every job gets its own fresh VM. Jobs are the middle layer in the 3-tier hierarchy. A workflow contains jobs, jobs contain steps. The default behavior, and this is where most beginners get surprised, is that all jobs in a workflow run in parallel. The moment a workflow triggers, GitHub looks at every job defined under the key and starts them all simultaneously, each on its own VM. This is incredibly powerful. If you have a lint job, a test job, and a security scan job, they all run at the same time. Your total CI time is roughly equal to the slowest job, not the sum of all three. The YAML structure follows a predictable 4-level nesting pattern. The workflow file itself is level 1. The key is level 2. Each job name, like or, is level 3. And under each job is level 4. The key is mandatory for every job. It tells GitHub which runner type to provision. Without it, GitHub won't know where to run your job and the workflow will fail immediately. Remember, multiple jobs means multiple fresh VMs, running simultaneously, completely isolated from each other. If a job is the machine, steps are the tasks you run on it. Steps are the smallest unit of work in GitHub Actions, and they follow two simple rules. They run sequentially, top to bottom, and they all share the same VM within their job. That second point is important. Unlike jobs, which are isolated from each other, steps within the same job share one file system. A file created in Step 2 is visible in Step 3. An environment variable set in Step 2 is available in Step 3. This shared context is what makes steps powerful. There are two flavors of steps. A step executes shell commands, bash on Linux and macOS, PowerShell on Windows. You can run a single line or a multi-line block with the pipe character. A step invokes a pre-built action from the GitHub marketplace or your own repository. The most common one you'll use is, which clones your repository into the working directory. Without it, your job runs on a fresh VM with an empty directory and no access to your code. The failure cascade is the other thing to know. If Step 2 fails, Step 3 and everything after it is automatically skipped. The job marks itself as failed and stops. You can override this with, which we'll cover shortly. Parallel execution is the default, but sometimes you need order. Maybe you want tests to run only after the build succeeds. Maybe you want deployment to happen only after both tests and security checks pass. That's what the key is for. You add it to a job to declare that it depends on one or more other jobs completing successfully first. When you write, GitHub won't start that job until finishes with a success status. If fails, the dependent job is automatically skipped. You can declare multiple dependencies with an array. This creates what's called a fan-in pattern. Multiple parallel jobs converge before a single downstream job can proceed. You can also create fan-out patterns. One upstream job completes, then multiple downstream jobs start simultaneously. Together, these patterns give you a DAG, a directed acyclic graph of job execution. GitHub reads your declarations and builds this graph automatically, running as many jobs in parallel as the dependency structure allows. The practical result, you get maximum parallelism where it's safe, and strict ordering where it's required. The best of both worlds. This is the most important concept in this entire chapter. Get this wrong, and you'll spend hours debugging. Here's the scenario. Job A builds your application and produces a compiled binary at Job B, which Job A tries to run that binary. Job B fails with file not found. You added correctly. Job B waited for Job A to finish. The logs show Job A succeeded. So why is the file missing? Because Job A ran on VM number 1. Job B ran on VM number 2. A completely different machine. When Job A's VM was destroyed, everything on its file system disappeared. Job B's fresh VM started with an empty workspace. The file never existed there. This is why and exist. They solved exactly this problem. In Job A, after building, you upload the output directory to GitHub's artifact storage. In Job B, you download that artifact before trying to use it. GitHub acts as the intermediary, a temporary storage layer between isolated VMs. The mental model to internalize controls timing only. It says wait for this job to finish. It says nothing about sharing files. File sharing requires explicit artifact uploads and downloads. GitHub Actions has two distinct knobs for controlling failure behavior, and they operate at completely different levels. Mixing them up is a common source of confusion. The first is applied at the step level. When a step has this set and it fails, the job treats that step as failed in the logs. You'll see the red X, but the job continues to the next step instead of stopping. The overall job can still pass. This is perfect for optional checks, an experimental linter you're evaluating, a code coverage threshold that's aspirational rather than mandatory, or a notification step where failure shouldn't block the pipeline. The second is, and it lives at the matrix strategy level, not the step level. Normally, when one job in a matrix fails, GitHub cancels all the other still running matrix jobs to save time and money. Setting overrides that. All matrix jobs run to completion regardless. This is invaluable for cross-platform testing. If your code fails on Windows but passes on Linux, you want both results before you go fix anything. Failing fast on a matrix would give you only one data point. The key distinction is about steps within a job. Is about jobs within a matrix. Environment variables in GitHub Actions work at 3 scopes, and they cascade from broader to narrower. At the workflow level, you declare at the top of the file, and those variables are available to every job and every step in the entire workflow. This is where you'd put something like that everything needs to see. At the job level, declared inside a specific job is available to all steps within that job, but not to any other job. At the step level, inside a single step is visible only during that step's execution. This is the right place for secrets. You pass a secret into exactly the step that needs it, and it's not exposed anywhere else. But there's a fourth pattern that solves a specific problem. What if you compute a value during one step and need it in a later step? Static blocks are set before the workflow runs. They can't capture values computed at runtime. The solution is the file. Any step can write a key value pair to this special file, and GitHub will inject that variable into the environment for all subsequent steps. The syntax is simply. It's a bit unusual. You're writing to a file to set an environment variable, but it's the standard pattern for dynamic values in GitHub Actions. While broadcasts a value to all subsequent steps, step outputs are more targeted. They let a specific step expose named values that other steps can reference explicitly using the step's ID. The pattern has 2 parts. First, a step must declare this is the name you'll use to reference its outputs later. Without an ID, there's no way to address that step's output values. Second, within that step's run commands, you write to the special file. The key becomes the output name. Any later step in the same job can then access that value with the expression. A practical example, a step reads the version number from your package.json and writes it to. Subsequent steps use that version to tag a Docker image, create a GitHub release, and update a deployment record, all referencing the same source of truth. One important note, if you're looking at older GitHub Actions documentation or repositories, you might see the command. This syntax was deprecated in 2022 and eventually disabled. It had a security vulnerability that allowed injection attacks. Always use the file approach. If you see the old syntax in a workflow, update it. GitHub-hosted runners cover the vast majority of use cases, but sometimes they genuinely aren't enough. That's when self-hosted runners come in. You install the GitHub Actions runner agent software on your own machine, a cloud VM, an on-premises server, even a Raspberry Pi. That machine registers itself with GitHub and waits for jobs. When a workflow targets it with, your machine picks up the job and runs it locally. The reasons to reach for self-hosted runners are real. If you're training machine learning models, you need GPUs that GitHub doesn't offer. If your tests need to hit internal databases or services behind a VPN, GitHub-hosted runners can't reach them. If you're running thousands of CI minutes per month, the cost of GitHub-hosted runners can become significant enough that running your own infrastructure makes financial sense. But self-hosted runners come with serious security implications you must understand before using them. The critical rule: never use self-hosted runners with public repositories. When a repository is public, anyone can open a pull request. If that pull request triggers a workflow that runs on your self-hosted runner, that untrusted code runs on your machine with access to your file system, your network, and any secrets the runner can reach. GitHub explicitly calls this out in their documentation. It's not a theoretical risk, it's a real attack vector. For private repositories with controlled contributor access, self-hosted runners are safe and powerful. Here's a fact that will save you real money: GitHub's default job timeout is 6 hours. 6 hours. That means a test suite that gets stuck in an infinite loop, a deployment waiting for a resource that never becomes available, or a Docker build hitting a network issue and hanging. All of these will silently consume hundreds of your GitHub Actions minutes before GitHub finally kills the job. The fix is a single line, at the job level. Set it to something that actually reflects how long your job should take, plus a reasonable buffer. For unit tests, 10 to 15 minutes is usually generous. Integration tests might need 30. Docker builds typically finish in 20. Deployments can vary, but 60 minutes is a reasonable ceiling for most scenarios. If a job consistently takes longer than your timeout, that's diagnostic information. Something is wrong and you should investigate rather than just raising the limit. Runner groups are an enterprise and organization feature that sits on top of self-hosted runners. They let you organize runners into named groups and restrict which repositories can access which group. This prevents a developer from accidentally or intentionally routing their feature branch build through the production deployment runners. You target a runner group by specifying both and under. It's a clean way to enforce separation of concerns at the infrastructure level. The matrix strategy is one of GitHub Action's most elegant features, and when you combine it with dynamic runner selection, you get something genuinely powerful: the exact same job, running on multiple operating systems simultaneously, without duplicating a single line of workflow code. The idea is simple. You define a matrix of variables under. GitHub expands that matrix into one job per combination and runs them all in parallel. The magic combination is using a matrix variable as the value for. When you write and define as a list containing ubuntu-latest, Windows-latest, and macOS-latest, GitHub creates 3 job instances each targeting a different runner type and starts them simultaneously. Add a second dimension like Node.js version 18 and 20, and now you have 6 jobs, every OS paired with every Node version. All running at the same time. You'll know within the time it takes to run a single job whether your code works across the entire matrix. Combine this with so you get complete results even if one combination fails, and you have an extremely efficient cross-platform testing setup. This pattern is how major open-source libraries validate that they work across environments. What used to require maintaining separate CI configuration for each platform is now a handful of YAML lines. Understanding the full lifecycle of a runner job, from the moment you push a commit to the moment the VM is destroyed, helps you diagnose slow workflows and find optimization opportunities. When you push, your job enters the queue. It waits there until a runner VM is available. For GitHub-hosted runners, this is usually fast, seconds to a minute. During high demand periods or if you've hit your concurrency limits, it can be longer. Once a runner is assigned, the VM boots and the runner agent initializes. This takes anywhere from 10 to 30 seconds depending on the runner type. macOS runners are notably slower to boot than Ubuntu. Then comes setup, clones your repository, or other setup actions configure your environment, and if you're using caching, the cache is restored from storage. After setup, your actual steps run. This is the work you care about. When the last step completes, post-run actions execute in reverse order, cache save happens here, artifacts are uploaded. Then the VM is terminated. Here's the insight: for a typical Node.js project, checkout takes 10 seconds, npm install without a cache takes a minute or two, and your actual tests might run in 30 seconds. The single biggest optimization available is almost always adding to save and restore your node_modules between runs. It turns that 90-second npm install into a 5-second cache restore. Let's make sure the most critical concept from this chapter is locked in. Here's the scenario. Job A builds a Go binary and saves it to the path on its runner. Job B is correctly configured with, so it waits for Job A to finish successfully. Job B then tries to execute that binary. What happens? Think carefully. Job B does declare a dependency on Job A. Job A did succeed. The syntax is correct. But here's the key question: where did Job A's file system go? Job A ran on VM number 1. That VM built the binary, stored it locally, and then was destroyed. Job B runs on VM number 2, a completely fresh, empty machine. The binary never existed on VM number 2. Controls execution order only. It does not copy files. It does not share storage. It does not connect the two file systems in any way. Job B will fail with a file not found error. The fix requires 2 additional steps. In Job A, after building, to push the directory to GitHub's artifact storage. In Job B, before using the binary, to pull that artifact down to the fresh VM. This pattern upload then download is the bridge between isolated jobs. Understand it deeply, and a huge category of confusing CI failures simply disappears.